Alright, welcome to the first online lecture video that I'm doing. So what we're going to be looking at today is we're going to be looking at what the periodic table can tell us. Our standards is this: obtain, evaluate, and communicate information about the use of the modern atomic theory, which we already learned about, and the periodic law to explain characteristics of atoms and elements. Especially what we're looking at today is the periodic law, especially just looking at the periodic table. Okay. So the question we're trying to hope to accomplish today is what can the periodic table tell us? What can it tell us about when we look at it? It can tell us a number of things, and so I'm going to show you that today. All right. Now, so here's our periodic table. All right. We got separated into groups, which is vertical columns. We got separated into rows. We also have it separated into families as well, different families that we have. We'll get into that in just a second. And also we have it separated down here in lanthanides and anthonides. Now, there's a number of things that the periodic table can tell us. If we look up here, the group numbers, they tell us something. The periods that are in these rows, that tells us something as well. Also, a stair-step line tells us something about the left side and something about the right side. You should learn that in physical science. Let's look into it. Okay. Now, we're going to get into this alkali metals, alkali earth metals, and all this kind of stuff, and knowing that kind of things and the families that we need to know about. So here it is. This is what information about atoms can be found on the periodic table. So first thing is the symbols. The symbols, sometimes the periodic table is not going to have the words written out. It's just going to be the symbols. And so that symbols tells us what it actually is. It's just the shorthand version of that chemical. It says the element symbols are either one or two letters. The second letter is always in lowercase. The first one is always uppercase. Okay. Do not get confused with I's and L's. A lot of kids do. They think that chlorine is Ci when it's actually Cl. So don't get confused there. That second letter is going to be lowercase, so that I would be a lowercase I if it was Ci, but it's Cl. So that's why it looks like an uppercase I. Okay, so the first letter is always uppercase or capitalized, and the second letter is always lowercase. Okay. Now these that we need to remember the symbols, and on your test you're going to have to know how to name symbols to chemical names or chemical names to symbols, and that's just memorization. Just focusing on when I give me a symbol or giving a symbol an equation, what is that chemical? Because we need to know that. Sometimes it will not be given to you. You have to find it for yourself, and so we're going to memorize this. And the letters kind of hint you to what the name says, anyways. So it really ain't that big a deal. But you need to know these. You need to know those 118 of them. Okay, all of them. And so that will be on your test, something you need to know. All right, so we can separate it into groups. All right, we can separate it into groups. So what is the groups? It's a vertical column on the periodic table. All right, meaning it's elements in the same group have similar properties. It's kind of like a family tree. They call it families as well. So families of elements. So if you're in that same group, so if you're in that same vertical group, that means you're going to have the same characteristics, just like your family has the same characteristics, or a lot of you have the same characteristics. Okay, so if it's in that family, it's going to have the same or similar characteristics. That can be a question on your test. Most likely will be a question on your test about which one has the most similar properties, and you find whichever ones are in the same families, the same group, the same vertical columns, and that will be your answers. Okay, so what are the names of the families? Well, first of all, we got alkali metals in group 1, which is right here. Group 1 starts here, group 1. And alkaline earth metals, which is also group 2. Now, this alkali metals, there's an exception. This H right here is not part of the alkali metals. The reason that hydrogen is right here is because it has one proton and one valence electron, and so it's right here in this group 1. And so alkaline earth metals, which all these alkali metals, alkaline earth metals, all these are metals. Groups 3 through 12, which is here, this dip right here, that is your transition metals. Okay. And then we can skip through these. It's called boron, carbon, and nitrogen family. But then we go over here to group 17. You need to know this, called the halogens. These are gases, and also the noble gases as well. You should learn some of that stuff in physical science about what those mean. The noble gases, they are stable. They don't need any more valence electrons. They don't need to lose or gain valence electrons. They're good. And so they don't really bond a lot of times with things. Sometimes it happens, but not a lot of times. Okay. All right, the periods. All right, periods are the cross row, left to right of the periodic table. So here's one period. Period 2 is right here. Period 3 right here. So on and so forth. So how many do we have? So 1, 2, 3, 4, 5, 6, 7. All right. Do we count these? Is that 8, 9? Well, actually, that's no. We don't count those. These are actually taken out of this spot right here, the periodic table. So really, if we was going to do it right, the periodic table should be actually expanded to way over here when we put these in that transition blocks section. Okay. So when you see these, they're taken out from here. So what is it? What period would it be in? Well, the first one, the lengthenized, would be in period 6, and the lengthenized. A lot of people get that confused. That this period 6 and period 7. Okay, so don't get that confused. Now, when we're looking at this periods and stuff like that, what does that actually mean? Well, look right here at this, and these periods tell us the energy levels. Okay, so if it's in period 1, it's going to be in the first energy level, which is right here. And when we get to quantum numbers, we're going to really look at this and electron configuration. All that stuff's going to make a lot more sense here. But just know that if this first period is at 1 energy level, if we're looking at the Bohr model, which we know is not exactly right, but if we're looking at the Bohr model, that would be the first ring. So the first ring would be period 1. If it had 2 rings, it would be in period 2. 3 rings would be in period 3, so on and so forth. Okay. And here's that idea. So period 1 in the Bohr model sense, like we said, we know it's not right, but it's a good way to visualize it. So period 1, it has 1 ring on both of these. Period 2, it has 2 rings, and period 3, 3 rings. Okay. All right, you see that? So periods tell you the number of energy levels, or if we're looking at Bohr model, the number of rings. Okay. All right. All right. So regions. There's 3 main regions in the periodic table. Actually, it could be 4. But metals, that's everything to the metalloid line except for hydrogen. So where is that metalloid line? So if we look here, there's our metalloid line, that stair-step line. Notice that aluminum is not part of the metalloid line. Okay, it's a metal. All right, but everything else that's touching the stair-step line is a metalloid. And so everything to the left is metals except for hydrogen, and everything to the right is non-metals. Okay, we got that? So everything to the left is metalloid of the metalloid line is a metal except for hydrogen. So why does these metals have positive cations? What they look at is once they're stable, what is their condition? Like what they want to be when they're stable. So if these cations have too many electrons, or they want to lose electrons to become stable, so if they lose those electrons, they have this positive cation. Why? Because there's more protons than there are electrons. So when these metals, all right, when these metals right here want to lose electrons, all right, to become stable, and we're looking at the octet rule here in just a second, but when they lose it, that means they have more protons than electrons. So every metal, all metals have positive cations, positive charges, okay? That's one thing about cations. Remember, positive means cations. All right, it's a cat. So Na is in group 1. So Na is in group 1. And we'll look at the trend here in just a little bit, but it's going to be in group 1, so that means the valence electrons, or the ion will be 1, and it's a metal, so it'll be a 1 plus charge. It'll be a cation of 1 plus. Alright. Now, nonmetals, everything to the right of the metalloid line, their bonding tendency, they tend to accept electrons. Okay? And so since they tend to accept electrons, that means when they gain electrons, they become more negative, and therefore we would have an anion charge, or anion for its oxidation number. Okay? So that'd be a negative number, negative charge. All right, so most nonmetals. Now there's only one exception to that, and it's hydrogen. It can gain or lose one electron. All right, so that's the only exception. Everything else, nonmetals don't have anions because they want to gain electrons to become stable. Why? Because they're on the right side of this periodic table. And so we'll look at that and just the reason why that's exactly true. Okay. All right, so like we said, metalloid lines are right here in the red. All right, everything that's on this as a stair-step line starts here, but the first step, all right, the aluminum, that one does not count. It's not part of the metalloid line, but everything else is. And then that's the great divide on the periodic table. The left side is metals, the right side is non-metals. All right, so here it is, the stability for atoms. Every atom wants to become stable. You need to know that, highlight that somewhere, that every atom wants to become stable. Okay, all right, they want to have the octet full. Okay. So there's the octet rule. It says every atom wants to become stable in an outer level. Outer level, That's the valence electrons. So the valence electron levels. This outside ring, when we're talking about valence electrons and we're talking about outer levels, it's this outside ring. If we're looking at the Bohr model and make it easier. So these outside rings are the valence electrons or the octet, the outer octet. Okay? All right, so when we're looking at stuff like that, that's what we're looking at. All right, the octet rule is dealing with this outer ring. So now, for S and P orbitals, which is like the first 18 atoms, they're stable at 8 on the valence electrons, and then it gets bigger and bigger besides that. But we can use this rule when we're looking at the periodic table. Okay, let me see if I have it up here. Right here. Okay, all right, zoom in a little bit. All right, so if we have, this right here, we look at it. There's charges throughout all this. A 1 plus charge, 2 plus charge, a 3 plus charge, a 4 plus 4 minus charge, a 3 minus, a 2 minus, a 1 minus, and 0 charge, no charge. You should learn that in physical science. And what that is actually oxidation numbers. And what that means is that when it becomes stable, this is the resulting charge of that atom when it becomes stable. All right. So because the electrons want to be lost here, that means they're losing electrons, and therefore they have a positive charge. All right. Because these electrons here in the nonmetals, they want to gain electrons, they're going to have a negative charge. And so that's how that works. So the octet rule, all right, is talking about that we can know what atoms that want to gain or lose based off of where they're at on the periodic table. So if they're in group 1, they want to lose 1 electron. If they're in group 2, they want to lose 2 electrons. Now if they're in group 17, because they're 1 away from becoming stable in that group 18, which is a stable group, all right, they're 1 away from becoming stable, they want to gain an electron to become stable. So this one gain an electron, therefore it's making a negative charge. Okay? So like right here, sodium and chlorine. So sodium's in group 1, all right? Chlorine's in group 17. So sodium wants to gain or wants to lose that 1 outer electron, while chlorine wants to gain it. Because look, 1, 2, 3, 4, 5, 6, 7. It has 7. To be full is 8. So it wants to gain that one. And by sodium giving its electron to chlorine, now if this loses its ring, and look at the second ring, it's full. It's a full octet. Every atom wants to become stable, and how you get stable? By having a full octet. Okay? All right. So that's how we work that. And so we can predict those types of bonds. All right, so predicting bonding properties. We can predict which elements would want to bond with other elements based off of their valence electrons and oxidation numbers. Okay, so if you have an oxidation number of 2, okay, or 2, like magnesium is 2 plus, like magnesium right here is 2 plus. All right, and oxygen is 2 minus because it's group 16. We'll look at that. Then they're going to want to bond pretty quickly. They're pretty good, they're very compatible in bonding because 2 plus, 2 minus, that's going to be a perfect bond, nothing left out, nothing left over, okay? But what if they don't match? What if it's not 2 and 2, whatever it might be? What if we have 3 and 2? Well, if that's the case, then we'll do what's called drop and swap. All right, make sure you understand drop and swap. Now, you should have done that in physical science. This is a lot of stuff that you should learn in physical science right here. We haven't really gotten into a lot of chemistry subjects yet, or mainly chemistry subjects, more of the basics of chemistry. So drop and swap, we'll have some practice of that in just a second. But all you do is take those charges, you drop them, and take off the charges. Drop them, drop the charges, and swap the numbers. All right, so just say, which one will these be? Just say if this had a 3 charge, and this had a 2 charge, so 3 plus charge and 2 minus charge, just if it was, it's not the case. But if it was, that 3 plus would come down here to chlorine, and that 2 plus would come down here to sodium. So it would be Na2Cl3. I'll show you an example of that in just a second if I get enough time. All right, so next one, oxidation and valence numbers. So valence electron numbers is just your group number. So group 1 is has 1 valence electron. Group 2 has 2 valence electrons. Now over here at group 13, which is the octet rule, right? So instead of having 13 of them, we can't have more than 8. So this is going to have 3. Just take that 1 off. Group 14 is going to have 4. Group 15 is going to have 5. Group 16 is going to have 6. Group 17 is going to have 7. And group 18 is going to have 8. All right, except for this helium, it's going to have 2. But it's going to be stable. Okay. All right. So for these oxidation numbers, it's this charge right, this trend right here: 1 plus, 2 plus, 3 plus, 4 plus, 4 minus, 3 minus, 2 minus, 1 minus, and 0. Okay, that's the trend for that. All right. Now these right here, okay. Those are the questions, and here's your answers. Okay. We'll talk about that more when we get done with this. I'll have an example on the board. Okay.